Hello everyone, I'm Dua here, Buteri, and here is my partner is.
I'm Nasser Al Azmi.
And before we start, I hope everyone in a good condition and stay safe. And I'm just want to say that you are a hero by just staying at home. And please do it. If it's not for you, do it for the one you love. So our presentation is a smart irrigation system, and I'm gonna start with the introduction. So, Internet of Things and automation is the goal of every engineering company, regardless it's new started company or large one. In those days, everything is connected to the internet and by default. Any new product will have the internet connectivity by default, not as an extra feature. So most of the leading company focus on industrial side or domestic side of the automation. But in this system, we as a team member will focus on the agriculture automation and its integration with the Internet of Things portion. So, and here we have our problem statement. Due to water shortage in most parts in the world, and considering that the irrigation is taking the largest part of the water usage, and there is a mass need for cheap and good quality food for the increasing number of population every year. From this point, no method should be taken into consideration when using water for irrigation. Most of the irrigation techniques depends on time and no real feedback about the soil moisture, which lead to over or under irrigation. Where the first case the water is wasted, and the second case the planets will not take the enough water. So our project idea is to design and implement a hardware and a software based on Arduino microcontroller to harvest the solar energy and probably store it in a rechargeable battery, which will be used later to energize the irrigation process in faraway places or farms. The system has an internet connectivity which will allow the user to monitor the harvest energy from the sun using the solar cells. Also to control the irrigation process into two modes. The first mode is automatic, where the irrigation will be started automatically on a low soil moisture level, and the second one is manually, where the user can start or stop the irrigation from mobile app. So here we have the general block diagram. I will not go into details. We will go to details after later. So I'm gonna start with the solar cells down there on the right. As you can see, it's connected to the power analyzer, and the power analyzer is connected to two ways. The first way is the controller, which is the Arduino, and the second way is to the charging circuit, and it goes to the battery and the voltage regulator from that. So, and when it goes to the Arduino, the Arduino is connected to the rotation motor and the Wi-Fi modem and the pump drinking circuit and the soil moisture sensor.
To achieve a system that will handle the irrigation process and make it very easy for the users regardless of their agricultural knowledge. The user can use his mobile application to monitor the following values: real-time soil moisture level, real-time cell voltage, real-time transferred power from cell to system battery. Also, the user can control the following specs in the system: the water pump on or off, the operation mode. In this slide, you have the system GUI, the graphical user interfacing. In the first, we have the three gauges up there: the voltage cell, power cell, and the soil moisture. So the user can read like the voltage and the power in the project we have, and the soil moisture in the real soil moisture that we have. from the sensors. And then we have the slider, which is the desired soil moisture, so the user can set the soil moisture that he wants, depend on the season or depend on the plant he has. And then we have the two bottoms, two modes. The first one is auto, which the system will irrigate automatically depend on the soil moisture that you set before. And then we have the manual mode, which has two options: the on, which will be on all the time, doesn't matter about the soil moisture, and off all the time. The hardware requirements. On the left we have the Arduino Uno, which is the most important part of our project, and it's considered like as a controller. Operating voltage 5 volt, flash memory 32 KB, the SRAM 2 KB, the EPROM 1 KB, the clock speed 16 hertz. And some people like the Arduino Uno is like most popular Arduino, as we know, because it's like a small board and which has like a lot of things. For example, the programming circuit, like power circuit and reset circuit. And then we have the ESP8266 built-in micro USB with flash and reset switches, easy to program, full input and output port, and wireless 802.11 supported. And then we have the first part that we are gonna explain of our project, the solar sensing and control circuit. So as we can see here in the middle we have the Arduino, and in the left we have the servo motor, which is like the servo motor is like a digital, and it has like 3 pins. The first pin is a signal pin, which is connected to D6, which is the digital side of the Arduino, and it like receive like logic 1 and logic 2. That's why it's connected to the digital side. And then we have the pin 5 voltage connected to the 5 voltage, and pin, the third one, is connected to the ground. And the servo motor will move the solar cell based on the information the Arduino get from the LDRs. So the LDR will see where is the light and send the information to the Arduino. Based on the this information, the servo motor will move. So on the first we have 3 LDRs, light dependent resistor. So I'm gonna explain how the LDRs work. So in the first we have the R1. The R1, when the R1 is receiving high light, the resistance of the R1 will be low, and then it's like when it receives like a light, it will convert it to resistance. So as we this is like a big problem because the pin A0, A1, A3, A4 and A5 are like analog pins, so they only read like voltage, and so that's why we make a voltage divider. We put 10 kilo ohm resistor connected to the ground, so we make a voltage divider. So when we have high light, the resistance of R1 will be low, and then the wire between the R4 and R1, the voltage between these resistors will be high, so the pin 1 will read high voltage, that's mean high light. When we have high light, the resistance of R1 will be low, so the voltage between R4 and R1 will be high. So the A1 pin A1 will read high voltage, so it will send information to the Arduino, and the Arduino will go and then will go to the servo motor, and it will turn to R1 side. And all the LDRs are working in the same way.
And here we have the Wi-Fi interfacing circuit. As we know, the Arduino Uno, it doesn't has the connectivity to the Wi-Fi, so we have to use the ESP8266. The ESP8266 is in charging of the it's in charge of the Wi-Fi connectivity, which is it will connect to the Wi-Fi, and it's gonna connect to the Internet of Things. And the purpose of it, it's gonna receive and send all the commands to the Wi-Fi and the Internet of Things. And so the ESP8266 is connected to the Arduino in pins D0 and D1, and the pins in the ESP is RX and TX. RX means the receiver, and the TX means the sender. So the Arduino gonna send all the commands to the ESP, and the ESP gonna connect it to the Wi-Fi. And here we have the power analyzer INA219. So the feature of it is senses bus voltage from 0 to 26 voltage, reports current, voltage and power, and it has a high accuracy. And here a picture of it. And here we have the solar power monitoring and battery charging circuit. So I'm gonna start with the solar cells, as you see in the top in the left. So the solar cells is connected to the power analyzer in the positive, the VA, the V plus. It goes to the pin 8, and the V minus go out from pin 7 to the post converter. So the power analyzer is connected to the post converter, and it's connected to the Arduino. So, and it's connected to the Arduino in SDA, and SCL is connected to the A5 and A4 in the Arduino. Even though it's connected to the analog side in the Arduino, even though it's connected to the analog side from the Arduino, it doesn't mean that the communication is analog communication. It's digital communication. But the Arduino Uno support the SDA and the SCL communication in these pins, the A5 and A4. So we have to connect it to these pins. And in order to the power analyzer to work, we have to set it to ground and 5 voltage, as you know. And we are using a lithium battery as in the top and the right. So and we connect a charge controller to the battery, so to prevent the over discharge and the over charge. And in order to the charge controller to work 100% efficiency, we have to get 8.4 voltage. And to make sure that we get all the time 8.4 voltage, we used the post converter. And it doesn't mean that we can get the 8.4 from the solar cells, but we want to make sure that we get 8.4 all the time. And it from the post converter, it goes to the buck converter, and it's gonna step down to the 5 voltage to make sure that we get 5 voltage for the circuit. And here we have the soil moisture monitoring and pump controlling circuit. Here we have the Arduino is connected to the water pump, and another way it's connected to the soil moisture sensor. So in order to the Arduino to read the soil moisture level, or the soil moisture number is from the soil moisture sensor. and the soil moisture sensor gonna read the soil and send analog value to the Arduino in pin A0. So when the Arduino get the analog value from the sensor, based on the soil moisture desired that we set on the app, it gonna work or not. If it want to turn the water pump on, it gonna send a logic 1 to the FET transistor to connect the wire to the ground, and the water pump gonna be set to work, and the water pump gonna be connected to 5 voltage and the ground, so it's gonna work. And if it doesn't want it to work, the Arduino gonna send a logic 0, and the FET transistor gonna disconnect the wire or the line from the ground. And we are using a capacitor, as you see from the water before the water pump, to prevent the noise.
This slide we have the flow chart. So when we start up there is manual mode. There's 2 direction. The yes direction, we will go to the manual mode direction, and when we say no, we will go to automatic side. So let's ask, like, say yes, we will go to the left side, which is the manual side. There are 3 options. The first one, serial pump on or off, and it will see if yes or no, the pump will be on, and then serial pump off, yes or no. If yes, the pump will be off, and then if no, we'll go down to serial auto mode, set mode to auto, and we will start over. And then let's start over to the up there manual mode. When we say no, we have 3. That means we have 3 options. The first one is serial manual mode, and when we say yes, we will start over and go to the left side, and then we have the slider value, save slider value. So in this option, the system will save the new slider value that you set, and then we'll start over and see if the pump will compare, like the pump will be on or off. And the third one is comparing the SD and SR. Before comparing these two, the system will read soil moisture and then compare them together. The SD means the soil moisture desired, and the SR is the real soil moisture that we have. So when the soil moisture, the SD is more than the SR, that means the pump will be on, will be on, and then we'll start over and see the soil moisture, and every 5 seconds. And when the SR is more than the SD, pump will be off, and then we will go down to read volt and power from the power analyzer, and then all the information will go to the app you have, as we can see here in this slide. Planck GUI. The Planck, this is the app we are using in our project. We use this app because of the ESP8266. So it's very easy to connect these two together. And as I said before, we have the 3 gauges: the voltage, power, and soil moisture. And then we have the slider that we can set the soil moisture we have. And then we have the 2 modes, manual and automatic. And then when you choose like the manual mode, we will choose off or on. Doesn't matter how the soil moisture is. And when we select automatic, it will be depend on the soil moisture that you set before. And benefit, monitor the soil moisture and just give the needed amount of water. Give a real feedback to the farmer regardless the distance. Reduce the cost on the farmer since the Wi-Fi is almost free. The education level of the farmer is not a matter since the system will use very easy to use application. The system can operate in manual or automatic mode. The farmer can start the irrigation to cool down the plant and avoid burning during the hot summer seasons. Future work. We have three suggestions about the future work. The first one is for better performance, the soil moisture sensor can be wireless sensor. In this case, more than one sensor can be separate all over a desired area. A solar tracker system can be upgraded to two-axis tracking system instead of one tracking system. So by saying one axis tracking system or two-axis tracking system, the one we have is one axis tracking system. That means the solar cell will move to two sides, left and right. But when we have two axis tracking system, that means we will the solar cell will go all around and all the sides. This will harvest more power from the sun energy. The land under irrigation can be divided into small zones, and each zone will be irrigated from separated water pump. Add a water level sensor to the water tank to give the user a clear vision about the remaining water quantity in his farm. The software can be upgraded to store moisture value during one irrigation period. So the users can view the history for the best result he has since he used our project.
And here we have our demo. We're gonna show it.
So this is how the solar system works.
So this is how the water pump work. It says automatic, and the moisture is 79, and if it's less than 30% the moisture soil, it will pump water. If it's more than 30%, it will
Not
stop.
pump water, yeah.
So it says 79, it will not work, and when you put it here, it says 0, and will turn the water will go through, and every 5 seconds it will be on. And we have another option, which is manual on off. It will not work. On, it will work. So it says manual off, and that's it.
Thank you.
And in the end, we want to thank our advisor, Dr. Dogda. He helped us a lot through this semester. Thank you so much, Professor Dogda. And that's it.